Okay, so this next bit is for AP Physics 2 only. It's a cool conversation, but it's not necessary to learn for Regents or AP 1. All right, you ready? So let's talk about the idea of flux. I have here a ring, okay? Now this ring, you can see my whole face in it, right? If I turn this ring, you can see less of my face. And the more I turn it, the less of my face you can see. Right now you can see none of my face through the ring. You can see it around the ring, but that doesn't count. So you can see full, none, some, right? And if this thing rotates, it would go from full to none to some to full to none to some. Okay, now imagine instead of my face, this were a flashlight. Okay, if I were shining a flashlight through here, you would have a maximum amount of light coming through the ring. And then you would have less light and less light and less light, and then here you would have no light coming through the ring. Okay? Now instead of a flashlight, imagine it's an electric field. Suppose I have an electric field going this way. I have maximum electric field through the ring. I have less, I have less, I have less, and now I have none going through the ring. They're just hitting the edge. So the amount of electric field passing through an area is called electric flux. And calculating it is very simple. It's the strength of the electric field times the area of the surface that it's going through, times the cosine of the angle, this one's a little weird, between the field and the normal to the plane of the area you're talking about. Equation looks like this. Okay, so this is called electric flux. And electric flux is an interesting concept. We're going to talk about magnetic flux later, which will be very important, talk about electromagnetism. There's luminous flux with light and things like that. So this idea of flux is pretty universal. But with electric flux, it allows us to look at something where the math is way over your head right now. It's not just calculus, it's calculus with vectors, which we call vector calculus. That's usually second year college math, but we can talk about the idea of it. And that idea is called Gauss's law. So this is from Carl Friedrich Gauss, and he was an incredible mathematician. And what he said was, if you have a surface, if you have a volume contained by a surface, the electric flux sticking out of that surface is equal to the charge inside the surface divided by a constant. Mathematically, it looks like this. That's not that hard, right? That's pretty simple. Electric flux is equal to charge divided by this constant called the permittivity of free space, represented by epsilon naught. Permittivity of free space kind of tells you how easily an electric field can expand through a vacuum, okay? So this epsilon naught, you find it on your reference tables in a couple of places. I told you not to worry about it earlier. Well, here it is. That's where epsilon naught came from. And we can take these two equations for flux and for flux and set them equal to each other. And that's where the funky math comes in. This is almost impossible unless there's a huge amount of symmetry. So we're only going to talk about it in terms of a sphere. All right? If you have a sphere, the radius of a circle, and then you have the circumference is 2 pi r, the area is pi r squared, the volume is 4/3 pi r cubed, right? But the surface area of a sphere is 4 pi r squared. And so if we substitute that 4 pi r squared in for area and do a quick little bit of solving, we get this. Okay, so what is that? That's the electric field for a point charge. That's a very small charge with some amount of charge plus Q. All right, so suppose I want to know the electric field a certain distance away, like out here, for example. This has a distance, we're going to call that R, right? And so if we draw a sphere, it's not a very good sphere, but you get the idea. If we draw a sphere around our point charge, and we take our electric flux equations and we set them equal to each other. One of them is EA cosine theta, because this is a sphere and the electric field coming out is always perpendicular. Cosine theta goes to 1, so we can just ignore that. Equals Q over epsilon naught. So this is what Gauss's law says. Q over epsilon naught is equal to the flux. Flux is EA cosine theta. So EA equals Q over epsilon naught. The area of this sphere is 4 pi r squared. So we get E times 4 pi r squared, that's a times, equals Q over epsilon naught. If we then divide this 4 pi r squared over to the other side, we get E equals, I'm going to write this slightly differently, 1 over 4 pi epsilon naught times Q over r squared. This is the electric field at this point. That's the strength of it. Now, if we said, well, what about way out here? I want to know what is the electric field at that point here. If we call that R2, we can just do that exact same procedure again. We draw ourselves a new surface, a new sphere. We repeat this exact math, and this ends up being an R2. So it turns out that for any given R, this is our equation. This is the electric field for a point particle. And it comes from Gauss's law. You can imagine that as soon as it's not a point, as soon as it's not a sphere, if it's some other weird shape, if you had a piece of wire lying there that you would put an electric charge on, trying to find the electric field at this spot is going to be really hard, because what is the area of the shape where the electric field is totally perpendicular? Even determining that shape is probably going to be something worm-like this-ish, but not entirely. And we're working in 3D here, so this thing is a ridiculously complicated shape. And then having to actually find the area of that shape is mind-breakingly hard. So 4 pi r squared for a sphere is good. That means we don't have to worry about this kind of thing. If you're dealing with a situation where you have a weird shape like that, as much as possible, what physicists like to do is zoom way out. If you have a shape like this and you zoom way, way, way out, it ends up looking like a point, like just a little dot. All right? So that's Gauss's law with a sphere, and that's as far as you need to know it. This is the equation for an electric field outside of a sphere that contains some charge. If you take that sphere and make it super, super, super tiny, like say the size of an electron or a proton, then this gives you the electric field contribution of a point charge, of a super tiny charge anywhere outside of it. Now, if that sphere is not super tiny and you're inside the sphere, well, the electric field is 0 if the charge is on the surface of the sphere, right? So Gauss's law tells us that the flux is equal to the enclosed charge divided by epsilon naught. So if there's no charge enclosed, there's no electric field. If there's charge outside, it doesn't matter. Inside, there'd be no electric field. But anywhere where there is charge, if you can draw a shape called a Gaussian surface, where the electric field is coming out of that shape perpendicular everywhere, and then do that complicated math, you can figure out how much charge is inside based on the electric field, or you can describe the electric field based on the charge inside and the shape of the object. So this is called Gauss's law. It leads to the voltage contribution of a point charge as well, which we'll get to in the next video.